So let's maybe, look back on what have we done in 6 amazing lectures of this class so far. So let me admit some people. Okay, so what have we done so far? Well, recall we used degree 2 certificates.
Professor, I think you need to share your screen.
Oh no. Yes, you're right. Amazing how I never get used to it. Wait, am I sharing screen now? I think I am. Okay, very good. All right. So, so far, what have we done? Well, we use degree 2 certificates, and we gave nice algorithms for max cut, and in fact, some generalizations, which I'm just going to call QP for quadratic programming. We also used degree 4 certificates, to approximate expansion. And then, in the last lecture, we saw how to generate and prove non-trivial properties of higher degree certificates. And in fact, used to design some new algorithms for some special cases of max cut, etc. So that's all, that's maybe some of what we have done so far. Actually, we did something more. In your homework 1, we in fact saw that the lower bound that we, or at least, this qualitative lower bound that that proves that degree 2 certificates are basically, as good as, so we analyzed degree 2 certificates as good as it can get. We used the cycle graph, the odd cycle graph, to show that, in fact, this is true, at least in a qualitative sense. And then we sketched that there is a generalization of it, which in fact, gives a precise quantitative correct trade-off, this Feige-Sheckman graph. And so, we also observed that degree 2 certificates analysis is tight. So in some sense, we know that degree 2 SOS cannot solve the max cut problem. And in fact, we precisely know what it can do, what's the best thing it can do. And then in fact, in your homework 1, you proved that, well, at least the example that proves that we analyze degree 2 certificate in the tightest possible way, well, can be broken by degree 4. And for this you use the square triangle inequality. You prove that odd cycle is not a hard example for degree 4 sum of squares. So, well, so just to summarize our state of understanding, right now we don't know if degree 4 SOS actually solves max cut. At least we have no idea of any instance that could potentially be hard, right? And similarly with expansion, right? Like we didn't quite prove a lower bound. We showed that at least the rounding technique we were using for degree 4 sum of squares in the context of expansion is more or less tight. That appears as one of the problems on your current homework. But beyond that, we don't quite have any reasoning to understand if we analyze even degree 4 certificates correctly for expansion. So for all we know, you could get a really, really good approximation, like a constant factor approximation for a graph expansion just using degree 4 certificates. So in some sense, it seems like even though we think some of this problem should be really, really hard, we don't really have strong lower bounds. We don't have a good understanding of when degree 2 or 4 or 6 whatever certificates do not exist. And so that is basically our goal today, to understand situations where we can rule out small degree sum of square certificates. In fact, we're going to rule out essentially omega and degree certificates. So we will prove things which are in fact extremely hard, maximally hard in a certain sense, at least within the sum of squares framework. So that's basically our goal today. So let's maybe summarize that goal as, how do we prove strong, convincing lower bounds on the sum of squares method. Good. And that's basically our goal today. By the way, before we embark on doing some cool math, I guess I need to point out the following important point. So this is a grad seminar. And I don't know if it is politically correct to say this, but I think there is going to be little variance in the grades eventually. So you don't need to worry too much about how well you're doing on the homeworks, etc. Um, and in that context, I would like to just maybe ask if you have feedback on how things are going, how easy, hard homeworks are they pedagogically useful? So for example, the reason for giving homeworks, at least from my perspective, is not to test you on anything, but actually serve as a continuation of the lectures. And so, many of these ideas are hard to understand unless you try to come up with new ones based on it, or prove extensions on it. So somehow each homework exercise is chosen to either further illustrate a point that we did in the lectures, or show some natural tightness of the analysis we did in the lectures. In general, all homework problems are supposed to teach you something. So you should feel free to give me feedback. I think it can be done anonymously on Diderot, so you can just try to make a post and make it feedback, and you can just let me know. You can also, of course, send an email. You don't have to use Diderot. And you can let me know how that's coming along. Are the homeworks useful? Are the lectures useful? What could we do better? Feedback is always useful. We are basically in the maybe the midpoint of our lectures today, so it's maybe a good time to ask for feedback. So feel free to email me, feel free to email Peter, feel free to send feedback through Diderot on all aspects of the class, on lectures, on usefulness of homeworks, etc. Good. Very good. Okay, so we can come back to the science/math of it. So our goal today is to prove a strong lower bounds on sum of squares. And as I promised, in fact, we'll end up showing that some problems are exponentially hard, which is um, not that much of a surprise. Perhaps somewhat of a disappointment that we will not be able to prove p equals np using sum of squares, but maybe that should not have been our goal anyway. So what problem are we going to show lower bounds for? Actually, in this lecture and in the next one, we will in fact show a bunch of lower bounds. The running example for today would be a very simple problem that generalizes, max cut in a way that we'll, I will discuss soon. The running example would be the K-lin problem over F2, which, also goes by the name of K XOR. And we'll discuss that in detail today. The other important goal of today, so we will start the discussion today, and we will prove things with just one goal of establishing strong lower bounds, on some problem, and to see how lower bound methods work, etc. But eventually we'll realize that we are proving not worst case lower bounds, that our lower bounds in fact have a stronger property. They are they would eventually end up as lower bounds on natural random instances of some of these problems. And so we will also use as an excuse to start our foray into average case average case analysis, average case problems, and usage of the sum of squares method in the context of average case problems. So what we will do is, like, today we will somehow proceed to understand the K XOR problem, which I'll soon define for you from completely worst case perspective. We'll prove a lower bound. Then we'll go back and, look at what we've done. And we will realize that we've done something stronger. We've actually proven a certain average case lower bound. And then we'll, use that use that as our main goal, for some part of, today's class, maybe towards the end, and then, all of next class and perhaps the next one too. So that's, our goal. So today's goal, in disguise, it's also to eventually introduce average case problems in the context of sum of squares method. So that's also what we will do. Good. So, but let's come back and let's look at what this K-lin/K XOR problem is. Okay. So it's very, very simple. This is just some fancy terminology for k-sparse linear equations over the simplest field you can think of, the field of two elements. Okay. Um, so, how do linear equations over the binary field look like? I'm just shutting down my programs because I'm getting scared that, Zoom might crash. Sorry about that. Okay. So, what are k-sparse linear equations? They're equations of the following kind. Okay. And I'm just like, circling my pluses to note that, these are additions modulo 2. So maybe I can, in fact, redundantly write that everything is being added modulo 2 here. Okay. So this is a k-sparse equations because this is a k-sparse equation because, the number of variables that appear with non-zero coefficients on the binary field. In fact, there is only one non-zero coefficient, which is 1. So the number of variables in each equation are, exactly equal to k. So these are k-sparse linear equations, okay? And that's the kind of object we work with today. So, well, it can be +1 or also, 0, of course. Those are the two values. And, as I said, this is addition modulo 2. Very good. So an instance of this problem is just a collection of equations, collection of, k-sparse linear equations. And, as usual, our goal is going to be to find an assignment to to the variables of the equation so that, as many as possible constraints are satisfied. Okay, so this is it. This is the k XOR problem or k len problem. Okay. But before going ahead, let me, make a notational switch for two reasons. One, that, we've been working over the +-1 hypercube, throughout this class. So we will go back and, look at this problem over the +-1 hypercube. So right now, the assignments are taking values in the binary field, 0 and 1. We'll make them + and -1. This would be completely notational switch. And then, we will just, formally state this problem and, set some notation to go on ahead with the class today. Okay, good. So the zi's take, values in 0, 1. How do you go to +-1? Not that complicated. So if we just, take z1 and map it to 1, like take this linear map, z1 goes to 1 minus 2 z1. And now, I'm suddenly going to look at zi's over the reals. So this map is working over the reals. And the reason I'm doing it is, like, even though the equations are over the binary field, the sum of squares method, etc., that we are working with, works over the reals. So our constraints better be real, polynomial equations, right? As, we've seen all throughout the first few lectures. So my goal is to, so let's maybe write it here, goal, notational switch to, work over the reals. Okay. So if I make this transformation, z1 goes to 1 minus 2 z1, then note that, 0, if z1 takes the value 0, then it actually goes to -1, wait, +1, sorry. And if it takes the value 1, then in fact, the transformed value takes -1. So this is good. This is exactly what we want. Our hypercube values are over + and -1. And if I look at the equation z1 XOR up to zk, then in fact, that gets transformed into a simple product over the reals of these 1 minus 2 zi variables. So let me just like write it like this. So let's call this x1. Okay, so I'm going to call the +-1 transformed variables as xi's. So this is simply I from 1 through k xi. Okay. Again, I'm doing really simple stuff, but I want to make sure that I don't lose you here. So notice that when is this side 1? When does this take the value 1? When when an odd number of zi's take the value 1. And you see that, that's the corresponding thing would happen on the right hand side. So this expression takes the value -1, which is the analog of +1 in this transformation, whenever an odd number of xi's are -1. Okay, so just in case if you were confused about this map, then that should settle it. Good. So so what have we done? We have actually mapped a k-sparse linear equation into a degree k monomial. So it's a degree k polynomial equation over the reals, right? So if we had an equation like this, let's call it, I don't know, b, the right hand side, then the equation, the polynomial equation on the right becomes, actually I'm going to write it like this. Let's say times 1 minus 2b equals 1. Okay, so now in this transformation, in fact, I'm going to claim equivalence. So, this right-hand side here, b, is either 0 or 1. And, if I go to the reals, then I transform 1 minus, make this transformation 1 minus 2b. And, I'm checking equality of these two expressions. And if they're equal, then both of them, either will be plus 1 or -1, and their product would be 1. Okay, so basically I have transformed this k-sparse linear equation over F2 into, a degree k polynomial, in fact, just a monomial equation over the reals. Okay, so I'm going to call this, for the rest of the the class today, I'm going to think of b's as always in plus minus ones. Okay, so I'm going to forget about the KXOR problem in the original way one might think about it, and simply think of KXOR problem as the following. So let's maybe formalize that. KXOR K-lin problem. The input to this problem is simply going to be a bunch of k-tuples. Let's call them C1, C2, Cm. These are k-tuples of variables. And each CI defines an equation. The right-hand side of the equation is going to be B1 up to Bm. And as I said, all of these are quantities in plus or minus 1. Good. And these are subsets of n of size k. That's what it means to be k-tuples. Very good. And each CI BI defines an equation that says that product of the variables that appear in the set CI times BI should be 1. Okay. So for each equation, so maybe I can draw a diagram to make it easy to somehow visualize. So so think of like a bipartite graph where I have m vertices on the right hand side, and each of these vertices somehow stands for one of the constraints. So I'm going to label each constraint by B1, B2, the right hand side of the constraint, Bm. And on the left hand side, I'll have the variables. And I'm drawing the left hand side smaller than the right hand side because that's the setting that we will work with today. The number of constraints will always be larger than n. We'll see why very soon. So this side is size n. It stands for the variables. And then, you just basically draw an edge in this graph if, some variable appears in the corresponding constraint. So if the first constraint is x1, XOR x2, XOR x3, then I have the 3 edges. And the label that I have on the vertex denotes the right-hand side. So maybe that's one way to, visualize this system of m linear equations, each being k-sparse. Okay, so that's basically how the input to this problem looks like. At least that's a notation we'll describe it in. And the goal, actually, before describing the goal, let me maybe set notation for value, etc. So I'm going to, in fact, call this instance, this set of all tuples, I'm going to call them I equals 1 through m. I'm going to describe them by script I. That's how my script I looks like. It just stands for, the collection of Ci, Bi, and they denote these equations as we just discussed. Very good. Good. And I'm going to, define I of x as the following polynomial. So this is still notation. I of x is going to be the polynomial. So it's an instance defining polynomial. It's simply 1 through m bi xi1 up to, oh, maybe I can just use, so, oh no, product j in ci xj. So, okay. So notice, what happens to I of x. So I basically, so this is a degree k polynomial, as you all have probably noticed, over the reals. And, it's input. So think of, giving it input as various Boolean assignments. So, my Boolean assignments are now in plus minus 1 to the n. So what happens to I of x? Well, if x satisfies all the constraints, then for every constraint, this product will equal bi. So their product bi dot this product would actually equal 1. So I'm adding m1s and averaging over them. So, I of x, in fact, is 1 if x satisfies all constraints. Okay. And if x violates all the constraints, then in fact, I of x is minus 1. Okay, very good. And in particular, the fraction of constraints satisfied by any assignment x, we'll call it val I of x, is, simply equal to half plus I of x over 2. Okay, I'm doing some crazy notation setting right now. I'm defining several quantities. We'll reap some of the rewards of this extensive notation setting today, but we'll continue to reap the rewards the next time. So, bear with me because we are going somewhere with this. Okay, so I just defined this, for every instance, I defined this degree k polynomial. And, that polynomial helps me define how many or what fraction of constraints does an, assignment satisfy. It also is a degree k polynomial. And, the final definition is opt I, which is, maximum over all x of val I of x, which is, basically saying, what is the fraction of constraints that any assignment can satisfy? What's the maximum possible fraction of constraints that any assignment can satisfy? Okay. Good. So, okay. So coming back, the input was, this instance I. We just defined, some quantities related to the instance I. We defined this polynomial ix. We defined val ix, and we defined opt I. And now, we can state the goal. The goal is given I, approximate val I. Oh, sorry. Yeah, approximate, approximate opt I. Okay, that's the KXOR problem. Good. We did some simple stuff. If there are any questions, feel free to stop me, okay? Like nothing major has happened, but, just in case.
Quick question.
Yes.
So why did your 1 minus 2 bi become a bi in the
good, yeah,
polynomial?
I made the great notational switch on you. I said that, instead of wasting my letter B over something that I'm never going to use, I'm just going to use B to denote the plus minus 1 version of B.
Oh, okay.
Okay, so that's this great notational switch, where I saved on alphabet. I only have 26 of them, so just wanted to be a little bit thrifty. Does it answer your question?
Yeah. I just somehow totally missed you saying that.
Yeah. I want to, I wanted to do this Boolean notation because you might see that version stated in many places. On the other hand, for our purposes today, it's better to think of them as this real monomial equations. So, there was some rationale for including both of them, but, we'll only work with this real version from now on. Good. So, very good. So, we have a problem in front of us. So we've got to discuss algorithms for it. So that's what we do. Good. So or actually approximating opti. So let's think about, think a little bit about basic algorithms for this problem. Okay, so suppose all the equations were satisfied. Okay, suppose there was suppose opt I happens to be 1. Then, in fact, I claim that there is a polynomial time algorithm for finding an assignment. So feel free to unmute yourself and tell me why. So this is a simple claim. I'm claiming that, if it happens to be true that, all constraints of all constraints in the instance I can be satisfied by some assignment, then in fact I can find such an assignment. Why is that true?
Misha doesn't seem to want to unmute himself, but he said because of Gaussian elimination.
Yeah. Okay, good. Misha is absolutely right. And the reason, as Misha said, is because, these are linear equations. And I hope you remember from, basic linear algebra, perhaps basic algorithms, that, linear equations over any field can in fact be solved in polynomial time via this really amazing algorithm, Gaussian elimination. And that, tells you that if opti was 1, then you can always find a satisfying assignment if there is one. By the way, I forgot, to make my usual request, but, if you could turn on your videos, that's great. Again, you don't need to, but if you can, that's always better. Good. So that's great. So all, satisfiable instances are somehow easy. But let's say, my instance is not satisfiable. Then what's, what can we do? How many constraints can we satisfy? What can we do when instance given to us is not, completely satisfiable? So, there's one algorithm that we saw in the context of max-cut when we started discussing, the max-cut problem, which was to, simply return a random assignment. What fraction of constraints does a random assignment satisfy, for KXOR?
Half.
Again, feel free to unmute.
Half of the constraints.
Right. Absolutely. Tim is absolutely correct. So in expectation, a random assignment must satisfy half of the constraints. If this is, somewhat mysterious, let me, this is an exercise in using our notation. So let's use it once. Okay. We'll do this simple proof only once. So, we are trying to understand the expectation over a random y of I of y. Remember that val I, like the fraction of constraint satisfied, is simply half plus half of this. Expected fraction of constraints satisfied. And so, we all, we just need to consider what this E of Iy is. And Iy was, if you remember, was 1 over m, I from 1 through m, bi product j in the ith k tuple of xj. And actually, my assignment is y, so let's call it yj. So by linearity of expectation, I get to, apply expectation here. Now, y is completely independent of the choice of the instance, right? It doesn't depend on bi at all. So this is in fact, this is the craziest amount of time I'm spending on this, but, just so that we are all okay with the notation. All I need to consider is what is expectation of the product of yi's, and yi's, each yj was a random plus minus 1. So the product, in fact, has expectation 0, right? So this is 0. Hope it's like absolutely super duper clear. And so, that proves that in expectation, the fraction of constraints satisfied by y is exactly half. Okay. So it's always easy to find a half satisfying assignment for, KXOR. In fact, this is, if you remember, the k equals 2. So, just to remind you, what happens in k equals 2 case? In k equals 2 case, our constraints are like, let's say CI is described by, the k tuple in CI is just I1, I2, so on. So if k equals 2, then my constraint corresponding to CI is simply xi1 times xi2 equals, bi, right? That's basically a two-sparse linear equation. Now, if bi equals, let's say, -1, for whatever reason, right? Then this constraint is just saying that, xi1 and xi2 should get opposite assignments. So this is a problem you've seen before. What problem is this?
Max cut.
Yeah, exactly. This is the max cut problem. You're trying to, maximize the number of pairs, that get pairs in your instance that get opposite assignments. So, this is no surprise that for k equals 2, it is actually just a special case. This for k equals 2, this problem, captures the max cut problem. In fact, max cut is simply, k-lin where all right-hand sides are, equal to -1. And so this is no surprise. So in some sense, what we just saw is like the analog of the random assignment algorithm for max cut, which was a random cut algorithm. So it's not much of a surprise that, that extends. But remember, for max cut, we were able to greatly beat half. We were able to what? Oh, that was a funny English sentence. We were able to beat half by a whole lot. Right? In fact, we were able to get a 0.878 approximate assignment. Right? So you can ask, well, now we have a generalization of the max cut problem. Can we do that here? So it turns out that, you may already have, experienced examples where the number 2 and number 3 are, very, very different. Here is one more example of it. So Hostad in 99, in one of his Gödel Prize winning papers proved that for all epsilon bigger than 0, it's NP hard to decide if a k XOR instance, so for all epsilon bigger than 0, for all k bigger than or equal to 3, a k XOR instance is 1 minus epsilon satisfiable. So this is, same as saying that this I of x polynomial takes the value 1 minus 2 epsilon for some x, or is at most half plus epsilon satisfiable. That's like saying that, for all x, I of x is at most 2 epsilon. This is just simple algebra, nothing complicated going on. I'm just like reminding you that our notation is helpful. So basically, Hostad proved that there is no way to beat this half approximate algorithm. Okay, this theorem statement that I wrote down here is simply, a way to state that, there is basically no substantially better algorithm, that can give you better than half approximation for, the max k XOR problem when k is bigger than or equal to 3. Okay. Now I wanted to notice that this epsilon, the slightly awkward seeming phrasing here of, introducing this epsilon, etc., is kind of needed because you already saw that if the instance is fully satisfiable, then there is a polynomial time algorithm to solve the problem. You can just do Gaussian elimination. What Hostad is saying is that, if you just like, take an instance which is almost satisfiable, like 99.9999% of its constraints can be satisfied, but not all, then, in fact, there cannot be an algorithm to find even like 0.51 fraction of the constraints that satisfies even 0.51 fraction of the constraints. So let me, write that as a corollary. If P doesn't equal NP, then there does not exist a polytime algorithm for finding 0.51 satisfying assignment to a 0.99999, okay, I'll stop there, satisfiable instance. So even though, you know, there was an assignment that satisfied almost all, but like a tiny but fixed constant fraction of the constraints, you can't even like satisfy 51% of them. Okay, that's what basically Hostad says. So for k bigger than or equal to 3, this problem, you know, is basically maximally hard. So let's, you know, in fact, make it a definition. So, you know, we'll basically say that k XOR, so, you know, in fact, I'm not formally defining this. I'm just maybe calling it a word right now. K XOR is, you know, so, you know, whenever random assignment is basically optimal, we call that, you know, problem approximation resistant. We'll, you know, we'll define this terminology a little bit better, you know, about an hour or so from now. But basically, you know, this is some way to say that, you know, the problem is maximally hard because really there is no way to beat like a completely trivial algorithm. So unlike max cut, there is no way to beat like the trivial, you know, random cut or random assignment algorithm. Okay, very good. So given that it's NP hard and, you know, we don't expect a polynomial time algorithm unless P, you know, is equal to NP, it's no longer, not much of a surprise that, you know, sum of squares should not be able to do this. But the nice thing is that we can prove a statement about sum of squares algorithm and, you know, existence of certificates without relying on, you know, hypotheses like P different from NP. We can, you know, give unconditional proofs that sum of squares, you know, will not solve this problem. Okay, so you can think of it as if for whatever reason you were, you know, you were convinced that sum of squares is the best algorithm in the world, that there is no better algorithm than sum of squares, then, you know, we can in fact settle P versus NP today. Okay, that's what we're going to do. So our class is really ambitious. Okay, so let's maybe say that. So today our goal is to unconditionally verify this for sum of squares. Okay, so in fact, more formally, we'll prove the following theorem. I'll describe the history of it in a second, and then also I'll write attributions here. But let's first state the theorem. So let, you know, let C be any constant less than 2. Then there's a constant, let's say some C prime, that depends, you know, on, let's say, K, like the K of the K XOR, and the epsilon that appear in Hostad, for example. So the constant only depends on this. It doesn't depend on n. That's important. So C prime of K and epsilon, such that, oh, and a family of K XOR instances. So, you know, this is basically a collection of instances for every n. So on every n, where n is the number of variables, you will construct one instance. This will be a family of instances, such that C times opt in minus I of x doesn't have a degree C prime n certificate for all large enough n. Okay, as you'll see, you know, this theorem, you know, again might sound too fancy. We are going to demystify, you know, how all of these, how each of its components work, etc. So this family, etc., would be very explicit. But let's first appreciate the theorem. What is it saying? It's saying that, you know, if you wanted to, you know, approximate, if you wanted to approximate, wait, Sorry, my bad. So if you wanted to approximate, the fraction of constraints satisfied by any assignment, that's like saying, so let's maybe parse the theorem. So what does approximation mean? Approximation mean that, you can somehow prove to me that val I x is, smaller than something. Okay. So in particular, if you were able to solve this distinguishing problem we wrote earlier, you would come up with, so in the case where, an instance is at most, let's say 51% of its assignment, 51% of its constraints can be satisfied, you will come up with an upper bound on val I of x. You will somehow prove to me that val I of x is at most 0.51. Okay. So in general, the problem of solving a kxor instance is same as, upper bounding val I x. This is the same stuff that we did in the context of max cut. And so, when you ask for certificates, that the best possible certificate would be to prove that val I x is always at most opt I. That's equivalent to proving that opt I minus val I is always non-negative, right? Now we hunt for special kind of certificates for this fact. So we hunt for sum of square certificates. So we can ask, so we know that this polynomial is always non-negative, right? Because val I x can never exceed opt I, this polynomial is always non-negative. We can ask, is there a sum of squares certificate for it, right? In fact, we can relax our goal. We can say, find me some certificate, which has some looseness in opt I. So I allow you to multiply this opt I by something to make it something bigger, okay? So opt I is always a positive number. It's not that hard to prove. I allow you to, multiply it by some constant c, which is bigger than 1, but at most 2, strictly smaller than 2, okay? And I ask, okay, maybe, you cannot find a certificate for opt I minus val I. Can you find it for c times opt I minus val I? Okay. And what we are seeing in this theorem is that, well, there is no, if you wanted a certificate from c times opt I minus val I for c, which is a fixed constant smaller than 2, then you need degree, which is omega n, because, there is no c prime n degree certificate for this problem, for this polynomial. Okay. So again, let me pause and make sure that this is clear, and take any questions. Okay. I hope that means that everything is clear. So yeah, so history, right? So I guess in the first class, I told you that, sum of squares, the algorithm, and, various issues about it were discovered in somewhat disparate fields, which were not exactly connected with each other in different contexts. So this theorem was, proven 2 times independently. So the first theorem, the first time it was proven, it was not at all an algorithmic result. It was what is called as a proof complexity lower bound. And it was proven by Grigoriev in 2001.
Hey, Pravesh, can you turn off the scribble setting? You have like the sync scrolling on.
Ah, good. I thought I had fixed it, but okay, too bad. Okay, good. I think I fixed the scribble setting. So the first time it was proven, this theorem, it was proven by Grigoriev in 2001. And actually, he wasn't even considering, he didn't, in some sense, Grigoriev didn't even talk or think about sum of squares algorithm. He was proving what is called as a positive Stellensart's proof complexity lower bound. We will actually see what that means. It's very simple. Now that we have learned a lot of things, it's very simple to describe what it is. We'll in fact do that formally in the next lecture. So let's ignore that for now. But he wasn't working in the context of algorithm design at all. And he proved this theorem. And it was later discovered in the context of, algorithm design and some like semi-definite programming, whatever, by Schoenebeck in 2008. In fact, Schoenebeck observed that this lower bound, in fact, implies lower bound for SAT and other problems, which also we will do today. But, he wasn't aware of Grigoriev's results, so he just like gave a different proof. Actually, it turns out that, at least in my opinion, Schoenebeck's proof is actually more complicated. It does something more general, but it's also more complicated. Like the proof you'll see today is like extremely simple, and it was Grigoriev's proof. And it's basically, maybe a 2-page long argument at best. So we'll do that complete proof today. Good. So that's the historical aspect of it. Very good. So, this C less than 2, etc. actually just basically, equivalently means that you cannot hope to beat random assignment using sum of squares. C prime and degree sum of squares. That's basically, an interpretation of this theorem. Very good. So we're going to basically, prove this. So we're going to just demystify every piece of this theorem now. So the first piece we will focus on is what family? Oh no. Sorry. The first piece we'll focus on is, what is this mysterious family of XOR instances? So now, if you've tried to prove NP hardness results, which I'm sure you have, then you might remember these contrived instances that we construct in our reductions. We say start from like an arbitrary weird 3x or 3-sat instance, and make some clever gadget to replace like small number of vertices with some other small number of vertices, and like describe how to somehow put clauses on them, and then we do some careful completeness and soundness arguments, right? Like you might have some memories of doing this at the very least in your undergrad. If not, well, I guess some of you are undergrad, so you may have already seen this stuff in either your TOC class, at CMU we call it undergrad complexity theory, or you might have seen it in your algorithms class. I'm sure you've seen these reductions before. And one complaint and potential downside of such reductions is that the instances that you cook up in this process can look somewhat pathological / contrived. And in fact, you might just take this bad taste from, your reductions, and you might say, yeah, kind of proved this problem hard, but not sure if it works for, nice instances. Maybe, only pathological instances are hard. Well, you probably would have less of those complaints today because, we are going to describe this family of KXOR instances, which, appear in this theorem completely explicitly, and they're going to be simply random instances. Okay. So let's describe what this means a little bit more carefully. So it's not, I guess the point is that it's not some weirdo pathological construction that, might follow from, some gadget reduction from 3-sat. It's going to be a very explicit family. So IN, so I have to describe you a family of, instances. So I'm going to describe you one for every N. So here is how I'm going to construct an N variable, instance in this family. I'm going to construct a random instance with about delta N constraints. Okay, so what does that mean? Here is how I'm going to, sample the constraints. So, pick every k-tuple Ci. Okay, let's maybe not call it Ci. Pick every k-tuple from N independently to be in IN with probability delta over N to the, let's see, k minus 1. Okay, very good. So how many k-tuples do I pick in expectation? Note that in expectation, so like there are about N to the k. Oh, sorry. Let's make it so like N choose k k-tuples. So let's maybe do it this way. Choose every k-tuple, to be in IN with this probability. I guess I was forgetting the difference between N choose k and N to the k. It won't matter eventually, but let's try to be accurate. Note that in expectation now, I have delta times N constraints. Right? Very good. And now, for every k-tuple so pegged, choose the right-hand side uniformly at random and independently. Okay, that's it. Output this collection Ci cross Bi from 1 through M. So let's say, here you put number of k tuples. Good, that's going to be my instance. I've completely described the instance to you. And now, I want to tell you what I'm going to prove about it. Okay, so I had to prove to you, that there are instances for which, I cannot actually find a degree 2 certificate for this C times opt minus I function, right? I've described the family completely to you. Okay. So now, I want you to, I want to explain to you, how do we prove that there is no degree 2 certificate, there is no degree C prime N certificate. Okay, so now goal, so next goal, to prove so how should I prove this? Again, like this is something that we saw in maybe, I guess, even the first lecture. We have to prove the non-existence of a certain object. Usually this is kind of a hard job, right? Like you have to prove that there is no way to write the C times opt in minus val in as sum of squares of degree at most C prime n polynomials. That's what you have to prove on the hypercube. In general, this is hard because it rule out potentially infinitely many possibilities. But in the first lecture we saw this basic duality theorem. We proved that in fact, if there is no sum of squares certificate of some degree for a polynomial, then in fact there is a certain object that exists. Okay, so that object we've been playing with quite a bit in the last few lectures. So duality implies that in fact, if this is true, if that this is equivalent to proving that there is in fact a pseudo distribution of degree C prime n such that the pseudo expectation under this pseudo distribution mu of this function is in fact negative. Yeah, you all remember this? So if there is no degree C prime n certificate, then in fact there must be a pseudo distribution that makes this polynomial of yours negative. So this rearranging is same as saying that under this pseudo distribution, val inx has a pseudo expectation which is bigger than C times opt of in. Right? Just rearranged. So basically, to prove this theorem, all I have to do is, prove that there is a pseudo distribution of some C prime n degree such that this val in, like this fraction of constraint satisfied by an assignment x polynomial, takes a value which is much bigger than C times opt in. And remember, C was, some fixed constant smaller than 2. So we are saying that, some 2, so, let's maybe call it 2 minus delta. So this is saying that, find me a pseudo distribution under which, equal mu of val inx is bigger than 2 minus delta times opt. Okay. Notice that, there is no actual distribution like this, right? I mean, we defined opt as the maximum of, val inx over all possible x. So over all true x's, val inx is at most opt in, right? Which means that over all actual distributions, the expectation of val inx should be at most opt in. But we are saying we still have to somehow find a pseudo distribution under which this expectation is about 2 times larger, or at least, something just below 2 times larger. Okay, so we can in fact prove that a random instance has this property. Okay, again, we are doing simple stuff, but because we are seeing this lower bound stuff for the first time, feel free to stop me and ask any questions that might be confusing / bothering, etc. I don't so I think we'll be comfortably able to finish the proof today, so we will likely not have to rush. So feel free to ask questions. Good. So that's our goal. So in order to make it even more concrete, let's calculate what opti looks like. So IN is now a fixed family of instances. So we can try to get our hands on opt-IN more concretely. We don't have to carry around this fixed number opti throughout the class. So let's just calculate what opti looks like. Okay, and then we'll make this theorem statement extremely concrete. So here is a simple proposition. So for some constant, absolute constant d, whenever delta is bigger than d over epsilon square. So remember, I sampled each constraint with probability delta n over n choose k. And this funny number was chosen just so that, in expectation, I have, about delta n constraints. Okay, good. So for some constant d, whenever d, delta is much bigger than d over epsilon square, opt IN is at most half plus epsilon with probability at least 0.99. Okay, so what am I saying? I'm saying that, if you basically, if you sample each constraint with some large enough probability, that's like saying that if I take large enough number of constraints, okay, and basically it's saying that if I take about n over epsilon square constraints up to constant factors, then the resulting instance, the opt of it would be at most, half plus epsilon with probability 99%. Okay, so it's like, arbitrarily close to half is basically the message. Okay, this has a very simple proof, so let's just like hack it out. And again, I'm doing such trivial proofs so that you get enough time to stop me and ask questions. I guess I'll stop doing it after that. After this, I'll just leave trivial proofs as an exercise. But let me do this one. Okay, so what am I going to show? I have to somehow show that opt-IN is at most half plus epsilon. That's like proving that no assignment satisfies more than half plus epsilon constraints. I'm going to do this one by one. I'm going to like rule out each assignment one by one. Okay, let's do it. So fix any assignment y. Okay, and now let's try to see what's the chance over the over the sampling of the random instance that this particular y turns out to be satisfying for the resulting instance. Okay, good. So consider the following random variable. It's bi product product j in ci, the ith constraint, yj. So why is this a random variable? So y is fixed, remember, okay? So I took like, so my constraints are ci, bi, remember? So now I took, the ith constraint, and the only randomness here is, due to bi. Okay, so I fixed y. Once I look at the constraint, the only randomness in this polynomial is due to bi because y is fixed. Okay, so this is a random variable. Okay, and I'm going to look at this I of y polynomial that we defined earlier. So I of y was simply the average of these polynomials for each constraint, right? So what's the expectation over the choice of b's of I of y? Well, we discussed this before. It's a similar kind of idea. Each bi is a uniformly random variable in plus minus 1. So the expectation of each bi times product of yj's is 0. And I of y is just an average, so the expectation is 0. Very good. In fact, the distribution of each of these terms here for a fixed y is simply of that of an independent random bit in plus minus 1. So this I of y is in fact just an average of m uniformly random and independent bits, right? Its mean is 0. And in fact, you can compute its variance also quite easily. It's actually equal to 1 over m. And because it's a sum, it's an average of independent random bits, I can apply the Chernoff-Hovding bound. And so I never recall the constants, but we'll not play with them. So this is saying that I of x is t times larger than its standard deviation. The chance of this event must be 2 times e to the minus omega t square. Okay, this is the Chernoff-Hovding bound as I remember it. It's saying that the chance that I take a value, chance that my random variable I of x, I of y takes a value which is t times larger than its standard deviation is at most 2 times e to the minus some constant times t squared. So now we are interested in the event that some y satisfies half plus epsilon fraction of the constraints. Well, that happens when I of y is at least some 2 epsilon root m. So let's fix t to be epsilon root m. Okay. So in that case, my threshold here has become epsilon. That's how I chose this. And then this probability becomes, for this choice of t becomes 2 to the minus omega epsilon square m. Good, very good. So now, this is for a fixed assignment y. I have to rule out all possible assignments. All I'm going to do is a union bound over the 2 to the n possible events. There are only 2 to the n possible assignments. So union bound means that, the probability that there is some y such that I of y is bigger than epsilon is at most 2 to the n times 2 to the minus omega epsilon square m. And so now we are basically done. I have to swallow this 2 to the n plus 1 factor with 2 to the minus omega epsilon square m factor. So choosing m. So if m exceeds n over epsilon square, then we are good. This probability is at most whatever, let's say 0.01, which is what I would like. And I can ensure that there are at least n over epsilon square constraints by again a simple Chernoff plus Hovding bound argument. So remember, I chose each constraint to be in my set with some delta n over n choose k probability. Again, the number of constraints I pick would be tightly concentrated around delta n. So if I again do a Chernoff plus Hovding bound argument there, this would happen with high enough probability. So I'm just gonna say here, so thus with probability at least 0.99 over the draw of the instance, opt I is at most half plus epsilon. Good. So again, are there any questions so far? Okay, yeah, this was simple stuff. So, but the simple stuff allows us to, state Grigoriev's theorem more concretely now. So here is a restatement of Grigoriev's theorem. Let, In be a random instance with, delta n constraints in expectation. That's how I'll write it. Of k XOR. Then for some C prime equals C prime of K. Actually, C prime of K and delta with probability at least 0.99 over the draw of IN. There's a degree C prime n pseudo distribution mu such that E twiddle mu of val I is 1. So what is this theorem saying? It's saying that, if you sample a random instance, okay, and it has, let's say, delta n constraints. This was an expectation, but, usually this, we could always condition on, we could always condition on event that, IN has about delta n constraints because things are tightly concentrated around that. So don't worry maybe too much about it. Then, this is saying that there is some fixed constant that depends on maybe like K and delta, but not n. Such that with probability 0.99 over the draw of the instance IN, there is a degree C prime n pseudo distribution. So when C prime is a constant, C prime n is, omega n. So there is an omega n degree pseudo distribution mu that thinks that, all the constraints of val I are satisfiable. Okay. So remember that when we discussed above, to actually prove a 2 minus delta gap, all we needed, was that E twiddle val I should be bigger than, 1 minus delta. But, Grigoriev does you one better. It basically produces a pseudo distribution which pretends like all the constraints are satisfiable. Okay, so maybe I want to make a note of this. Now, this can be somewhat disconcerting at first, okay? We saw a very simple algorithm that can at least check if an instance is completely satisfiable, right? You can do Gaussian elimination. If you find an assignment that satisfies all the constraints, the val I is 1. Otherwise, val I is strictly less than 1, okay? But what this particular theorem is saying, as one tiny corollary of it, is that if you wanted to replicate the guarantees of this Gaussian elimination algorithm that runs in fixed polynomial time with the sum of squares algorithm, then in fact you need to spend 2 to the omega n time. Like, the only, like the degree required to somehow discover that val I is strictly smaller than 1 is actually, at least C prime n. So it can be quite weird, right? Like we are teaching a whole seminar on this algorithm because we think it's quite strong, can do things. But here is, this theorem that's saying that it can't even do Gaussian elimination. It can't even solve linear equations. So some people, like to summarize Grigoriev's theorem as saying that SOS can't even, solve linear equations. Okay, and it is what it is. It cannot. What can we do? Good, very good. So we will actually prove this theorem today. Okay, we will actually construct such a pseudo distribution. Okay. So our goal okay, and as I said earlier, there is clearly no actual distribution, right? Like so this is this is in some sense a pseudo distribution that whose properties can never be replicated by an actual distribution. This in some sense could be thought of as like some strong difference between pseudo distributions and actual distributions. So one way to state it is that if the pseudo distribution had degree 2n, then certainly it would know what the true value of the instance is, because degree 2n pseudo distributions are actual distributions. This theorem is saying that if you make this 2n, the degree 2n, into like C prime n for C prime which is sufficiently small constant, well, then, the pseudo distribution doesn't even know that the instance is unsatisfiable. Okay. I'm just repeating the conclusion in like different ways just to, give you a sense of what's happening here. Very good. So, how do we construct such a mu, right? So we are getting to this task of constructing a lower bound. We have to construct a pseudo distribution mu. How should we do it? So let's maybe just try to, let's try to just, describe. So, so remember that if I want to describe a pseudo distribution, I just need to describe to you what the values for all monomials is, right? Because then I can extend it to all polynomials linearly. And in fact, I just need to describe to you its values, the expectations values on S, which are at most, C prime n sized. Why is this enough? Well, we proved earlier. So why? So we proved that, mu is a pseudo distribution if and only if, e twiddle mu is 1, and for all polynomials, p e twiddle mu p square is bigger than or equal to 0, whenever degree of p is at most c prime n by 2 of degree c prime n. Right? So in some sense, the only two properties I need to check for the pseudo distribution is, well, the first is usually easy. The second property is saying that, the pseudo expectation of all squares of at most c prime n over 2 degree polynomials should be non-negative. And this is the fact only about, degree at most c prime n polynomials. So it's enough to describe only, what happens to c prime n degree polynomials, c prime n degree monomials. I don't even care what happens beyond it, right? So you're all with me when I say that, it's enough to describe these numbers. Very good. Of course, here, we don't just want to construct any pseudo distribution. We also have to, satisfy that mu, e twiddle mu of val I is 1. Actually, this is same as saying that e twiddle mu of half plus this polynomial I x over 2 is 1. Which is if and only if e twiddle mu ix is 1. Good. So I have to give values to all possible monomials to describe this object. Let's try to do that one by one. Let's try to give values to every monomial one by one. Okay. So I have to make, e twiddle mu of ix 1. Okay. What value? So the first, like, interesting set of monomials are basically, the ones that correspond to constraints. So let's look at them, right? I have, let's say, I have constraints. So I had constraints ci comma bi, right? And each of these constraints meant the following polynomial equation. Right? So I have to satisfy, so e twiddle mu of ix equals 1 means that, so let's maybe just recall this notation. Right? So this is one of the monomials that I have to give a value to. So let's consider what value should we give to it, right? This is a degree k monomial. What value should I give to it? Well, if I have to satisfy, if I have to satisfy this inequality, I have to satisfy this equality, I claim that I must give it a value. I must set e twiddle mu of to exactly equal bi. Okay. Notice that this assignment, this value is good enough for this equality to hold, right? Because I get 1 over m sum I from 1 through m of bi squared, and bi squared, no matter what bi is plus or minus 1, it's always 1. So I satisfy this constraint. So I can, this set of value, does satisfy, my goal here. But in fact, there is no other value. Okay, I cannot actually do anything else. Why not? So for example, one thing you might want to do is, maybe like try to give one of the monomials a larger value in magnitude. Let's make it like 1.1 bi, and give all the other monomials maybe somewhat tinier values. That would also be a way to satisfy this equality constraint star here. But I cannot quite do that. Can someone quickly tell me why not?
You have Booleanity constraints on X side.
There are no constraints in our pseudo distributions. That's out of syllabus. We've never defined, well, okay, I told you on Diderot what constraints are, but we are supposed to use in lectures only things that we did in lectures. So even though your answer is correct, you get -1 points.
Cauchy
Okay.
Schwarz.
Right, yeah. So there are various ways to reason. So I think Praneeth just pointed out that we can do Cauchy-Schwarz, but we don't even have to, I mean, in some sense, that's equivalent to everything else I'm going to say, but I'm going to use like a a robust argument that I can use multiple times. So let's reason. So let's call this monomial, because I have to write it so many times, as just x sub ci, okay? So why can't I set it to 1.1 bi? Well, remember in last class, we used the following nice property of, pseudo distributions. So recall. So what did we say? We said that, for if so here is what we proved the last time, that mu be a degree d pseudo distribution over the hypercube. Then for all sets of variables s is at most d over 2. The marginal mu restricted to the set of variables s is in fact an actual distribution. Right? That's what we proved the last time. So now, I'm trying to construct a C prime n degree pseudo distribution, right? In particular, the number of variables in CI is like k. K is much, much smaller than C prime n. It's a fixed constant. So the marginal of mu restricted to the variables in CI must be an actual distribution. And there is no actual distribution over variables in CI that makes the monomial take a value which is bigger in magnitude than 1. Right? In fact, under every actual distribution on variables in CI, the value of the monomial x sub CI is +1 or -1. Okay. So there is no distribution that can make this happen. So this is not legal. We can't quite give it a value 1.1 bi. Hope that made sense. Okay. We're going to use this local distribution argument again and again now, but this was the simplest use of it. That's good. Very good. Okay, so what have we learned? So conclusion of this discussion is that, e triple mu of x sub ci must be equal to bi if I want to, construct a pseudo distribution like I want. Okay, very good. So now, let's look at some more interesting monomials. Okay. Let's look at so let's say, ci and cj are two constraints. So I guess constraints are defined by ci bi and cj bj. Let's look at the monomial, which is the product of xci and xcj. Can someone tell me what I should set this to? Again, I claim that I have no choice on this. What should I set?
BJ.
Pi times bj, and I have no choice. So Tim, while you're unmuted, can you tell me why I have no choice?
Oh, well, because if you multiply these two classes, you get another class.
Yeah,
right.
That's
yeah.
absolutely correct. And just to complete that argument, again, the union of ci and cj is at most 2 times k variables. So mu restricted to the variables in ci union cj has to be an actual distribution, because mu is a pseudo distribution of degree c prime n, right? Much, much larger than 2 times k. And if I take any actual distribution where expectation of xci is bi, expectation of xcj is bj, then the expectation of xci times xcj must be bi times bj, right? You all understand what this means, right? Like, what does expectation of xci being bi mean? It means that the local distribution of mu on ci is supported only on those x's that make the parity of the variables appearing in ci equal to whatever bi dictates it to be. Okay, so the parity of the variables in xci is fixed. The parity of variables in ci is fixed, the parity of variables in cj is fixed, and any distribution that fixes those two parities must also fix the parity of variables in ci union cj. Okay, again, please feel free to stop me if this is not making sense, but I hope you understand that my hands are tied here. I cannot do anything except give these values. So what can I do? This is going to be the value. Okay, very good. So now we'll basically abstract out this reasoning and look at all the monomials where our hands were forced. Okay, let's try to formalize this idea. So here's the definition. Degree D derivation. Okay, and this is just going to collect all the monomials where my hands were completely tied, where I have no options. Okay, so in fact, let me describe it as a process. Okay, instead of like a collection of just like constraints, let me describe it as a process of generating such constraints. Okay, so so let's maybe say the following. Let DERD be the output of the following algorithm or following process. Okay, and this is the definition. So define. So add in steps 1 through m, add xci equals bi to this set DERD. Okay, and now in let's see, just traverse all monomials in a fixed order graded by degrees, and if so, let's say you found a monomial for every let's say monomial xu in this order, check if this DERD set contains constraints like this. Okay, this is a long English sentence, but it's saying something very simple. So let me read it out to you. Saying, just like traverse all. So I start by, putting the constraints of the instance I, the corresponding monomial constraints, into my set DERD, the set of derivations. Then I just traverse, all monomials in, order which is like graded by degrees. So, just fix an arbitrary order and like go over all possible monomials. Just maintain the invariant that you have like lower degree monomials coming before the higher degree ones. Do this in this order. Well, let's say, you're looking at monomial xu and you're trying to decide if it's, if your hands are forced on xu. So just try to find if in the set of derivations you've built so far, if there is some constraint xs equals b sub s and xt equals b sub t, which is already included in the set of derivations, and s and t satisfy that, you can basically derive the constraint on x sub u from them. Okay, so this s xor t is the symmetric difference of the set Okay, so notice that if this is true, then I can derive x sub u equals b sub s times b sub t. And so I derive that and add it to the set der d. Okay. The reason I'm using this funny notation O plus for symmetric difference is because I already used up delta, which might be the standard notation for symmetric difference. So we are stuck with this notation. It's actually somewhat reasonable to call it circle plus, but let me not justify it right now. Maybe all of you see it already, but let's ignore that. Good. So I just formalized this reasoning we were doing earlier of setting up some constraints, setting up some values of mu on which our hands are completely tied. We just like derive this as a process here, and of course so we are only looking at degree at most d monomials because that's what we are interested in. Okay, very good. So I guess here is, so we can make it maybe a definition. Good. So this is all great, but there is some real weirdness going on here. Somehow, there is a reason why this process might be ill-defined. So I guess, can someone unmute themselves and tell me why this process actually so far is not even well-defined? So we made a definition, so everything is going as per plan, but actually, this is misleading because this traversal business I just, described is not even well-defined a priori. So
Misha kind of has the answer in the chat.
okay.
He asked the question. It's like you could get that like you could have two different derivations that try to set the thing two different values.
Yeah, absolutely. Misha is absolutely correct. And sorry, I did not see the chat, Misha. The reason this is this could be potentially bogus is because I looked at this monomial u and I tried to check if there is some pair of constraints that derive xu. But what if there are two different pairs? If there are two different pairs, they dictate two different values for x sub u. And then I don't know what to do. This process is bogus. We'll actually prove it's not. Okay. So that's what we will resolve in a bit. We'll prove that this process is well defined and does interesting things. So let's see what's a good thing to do. Okay, we can maybe define this and then take a break. So let's maybe point out this issue. What if there are two different conflicting derivations for x sub u? That's the problem that Misha pointed out. Before, I use it as my punchline, but okay, good. So we'll argue that in fact, we never run into this conflict, okay? So we'll show that we will never run into a conflict. Okay.
Is this with high probability?
Good. Yes. This is going to be with high probability over the choice of the random instance I sub n. Jason is absolutely right. Yeah. So, there could be bad instances, but, for our random instance with high probability over the choice of the constraints we chosen it, this will never happen. Okay. And the way we will do it is by doing some, very simple, mild combinatorics. Okay. So fun stuff ahead. So new definition. So, I'm going to characterize some combinatorial property of this random, instance that we built. And I'm going to relate the existence of conflicting derivations to, this combinatorial property. And then we'll argue that this property, in fact, is satisfied. Okay. That's what we'll do. So this property, in fact, there are reasons to study this property beyond, proving lower bounds for XOR. But again, we will not do that today. This is called hypergraph expansion. Here is what it means. So this is, okay, this may appear like, nothing to do with our instance so far. We'll do it very soon. Let me make this definition and then, relate it to our instance. So a K uniform hypergraph, remember what that means? It's just, a collection of sets of size K over the vertex set 1 through n, okay? So maybe I can say that set of all set, some subset of K size sets in this, that's what it means, is said to be T comma beta expanding if for every subset, okay, let's maybe give this a name. What should I call it? Okay, I'm gonna call this, there are no complex numbers in our lecture, so I'm gonna call this like weird C today. So it's gonna be T comma beta expanding if for every subset, C of at most T edges, the symmetric difference, okay, I'll actually describe what this means in a second. So this is basically the, no, actually, a second. Okay, maybe I can just describe it this way. This union of all all the hyper edges is at least beta times the size of beta times the number of hyper edges. So what is this saying? Okay, so the notation can be somewhat daunting. So let's be clear about what this is. So I'm saying that this K uniform hypergraph H that I have is said to be T comma beta expanding. If I take any T of its hyper edges, so remember each hyper edge is just a collection of K size, a collection of K indices from 1 through n. If I take the union of all these indices, okay, in this collection, script C or whatever, then on an average, so if I take the union, on an average, each CI contributes, about beta unique indices from 1 through n. So union is not too tiny. The union contains, at least beta times, the size of C number of indices from 1 through n. Okay, like, if this definition is somewhat confusing, think of, 3 uniform hypergraph like this. So, if I look at 1, 2, 3 and 1, 2, 4, then there are these 2 hyper edges. If I take their union, they contain 4 unique indices, right? While there were 2, while there were like 2 distinct hyper edges. So this satisfies the inequality above with like, beta equals 2. Just in case, that was confusing. But that's what it says, right? So in some sense, this condition, what is it saying? It's saying that, that if you take any not too large a number of hyper edges, then in some sense so there cannot be too many intersections between them, is maybe the point, that somehow there are going to be somewhat a large number of unique indices that must appear in the union of these T hyper edges, at most T hyper edges. Okay, very good. So good. Let's see. Okay. Sorry. So here is how this is related to us. Here is how this is important to us. So what's the hypergraph we have here? Well, so remember in the random instance I sub n, we chose the subsets of variables that appear in each of the equations at random, right? So we called it C1 up to Cm. So that's a K uniform hypergraph, right? On the vertex at 1 through n. So here is what we'll prove about it. So actually, let's maybe write it like this. Let In be a random instance with m m constraints. Then for all for L delta fixed constant delta bigger than 0, there exists an eta, which eta depends on delta and small delta, such that with probability at least 0.99, the hypergraph is eta n comma 2 minus delta expanding. Okay, it means that if I take any subset of any set of constraints, as long as I don't choose more than eta n constraints, if I take the union of the variables appearing in those constraints, then on an average, each hyperedge, each constraint contributes almost 2 unique variables. Okay. Sorry, I guess I've shifted to so let's focus on the case of k equals 3 here, just so that I don't have extra notation. Okay, that's why this 2 minus delta. Otherwise, of course, there's something, so there should be some dependence on k. So, we'll just focus on this part, we'll just focus on proving it for k equals 3. The things just work out, in an analogous way for, larger k2. So let's focus on k equals 3. So what they're saying that, if I take a random 3 uniform hypergraph corresponding to the, instance I sub n that we cooked up, as long as, it has some delta n constraint, there is some eta that depends on, this density of the constraints in my hypergraph and the small delta which appears here, saying that for this fixed constant eta, if I take any collection of at most eta times n constraints, then their union contains 2 minus delta variables on an average per constraint. So let's maybe say this: each constraint contributes 2 minus delta unique variables on an average. Okay, and that's what this proposition is saying. In particular, this hypergraph C1 up to Cm is eta n comma 2 minus delta expanding. Okay.
Is there anything special about 2 in this?
Yeah, actually, it's an excellent question. You'll see that you can only construct hypergraphs which go up to 2 expanding. You can actually never match 2. You can get arbitrarily close to 2, and you certainly cannot match 2 or go above it. So yeah, there is something special about 2. So for k, for example, this would be k minus 1 minus delta. So maybe that was the implicit question. Okay, so if I look at a k uniform hypergraph with omega n edges, then I can ensure that it is eta n comma k minus 1 minus delta expanding. In fact, you can ask for the trade-off between delta and eta and small delta, and there is an interesting trade-off which actually we might quote but not prove in the next lecture. So does that answer your question, Jason?
Yeah, thanks.
Okay, good. So what happened? So, we were worried about the conflicts in our definition. And then I said that, we're going to use some combinatorial property of a random instance in order to prove that there cannot be any conflict in this, definition of hard constraints, or like this constraints where my hands are tied that we defined. Okay. Then we define hypergraph expansion, and we proved that, the random instance, the corresponding hypergraph is, somewhat expanding. But I haven't explained to you, why that is useful. what we'll do now is like take a 10-minute break. Then we'll come back and see why it's useful. We'll also, complete the proof of Grigoriev's theorem. And then, we'll see some connections. But, for that, let's wait until the end of the break. So, we'll let's say reconvene at 5:53. That's 10 minutes. Usually it's 5:55, but, let's aim for 5:53. So let's, begin again. So, this proposition is saying that, if I take a random instance, then with like 99% probability, it's going to be eta n comma 2 minus delta expanding. That just means that, if I take any at most eta n hyper edges, then, they will collect at least, 2 minus delta unique variables on an average per constraint. Okay. So we will prove, this proof is also just a Chernoff and union bound kind of argument. So we'll prove this at the end, depending on, how much time we have, so that, we get to make the important points, before we spend our time doing union bounds. So let's just, use this proposition and move on to prove why, at least, there cannot be a conflict in our, derivation that we defined earlier. Okay. So let's call this a lemma. By some slight abuse of notation, we call the instance itself expanding if the corresponding hypergraph of its constraints is expanding. I hope that's not too bothersome. So suppose C1 up to Cm is, so now, I am going to exclusively focus on the case of k equals 3, because for whatever reason, I have done that in my notes. So that's basically, what we'll do. Although, the proofs are entirely the same if you go to larger k, nothing really changes. Okay. So suppose C1 through Cm is a eta n 1.7 expanding hypergraph. And I just chose 1.7 because of no good reason. It's a number which is bigger than 1.5 and smaller than 2. I was allowed to choose any number smaller than 2. And you'll see that I need a number bigger than 1.5. And I don't know, I just picked 1. Okay, so let's say that, suppose C1 to Cm is 1.7 expanding. So only need this to be bigger than 1.5 and less than 2. So in this, I guess, just to remind ourselves that that's all I wanted. Very good. Then there do not exist conflicting derivations. So that do not exist S1, T1, S2, T2. Okay, this is again an abuse of notation, but I think you understand. So let's maybe say then. There do not exist S1, T1, S2, T2 in their D, such that S1, T1 equals S2, T2. So it's saying that, if I do degree D derivations and D is, some constant factor smaller than this limit of where the expansion holds in the hypergraph, then in fact, there cannot be any conflicting pair of derivations. Okay. Notice that, this is saying something stronger than what a priori we might have needed. Actually, even if there is a conflict, if the conflicting derivations give me the same value, I'm not that worried, right? If for whatever reason, these two happen to be the same, but also B sub S1, B sub T1 happen to be equal to B sub S2 times B sub T2, I don't actually give a conflicting value. But, I'm just proving that in fact, there is no conflicting pair period. I don't even care about the right-hand sides. Okay, so just to notice that this is a little bit stronger than what we might have needed, although really not that much, because I think you can prove that if there is a conflicting pair, in fact, there must be, an assignment that must be conflicting that I make to them. So this not much different, but formally, I'm proving something stronger. Very good. So why is that? Let's prove this lemma. So the way to think about it, at least, one nice way to argue this is to go back and remember something else about our derivations. So remember how we, defined this concept of a degree D derivation. We first, added all the clause or like all the actual constraints in our I and the corresponding monomial values to it. And then, we said, okay, if we basically, in some fixed predefined order, we picked two of the already derived constraints and derived a third one from them, right? So one consequence of this process is that every constraint that exists in this set of derivations is in fact associated with the union a union of clauses, right? Like somehow every constraint that exists in the set DER is obtained by just XORing out a bunch of clauses. Okay, so I hope that is clear. Maybe I can make this point here. Note every constraint is associated to a union of clauses here, a union of constraints from the instance. Very good. So we'll use this freedom or use this simple fact. So let's say that we had, so what does the hypothesis mean? That like we had already derived all these constraints in the set of derivations, right? And in fact, each of them is associated to some union of clauses. So let's call it U1, U2, let's say U1 prime, U2 prime. So, we'll argue some nice property of the clause sets that correspond to the hard constraints that we generated in the set of derivations. Okay. So here is what we will argue. So here is a claim. Suppose U1 up to UR are all the clause sets or set of constraints from I that appear in the derivations. Okay. Then for all of these i's, ui is at most 10 times d. So remember, like d is the degree of the derivation we are doing. So d is at most some eta n over 100. We are saying let's look at so each constraint that we put in the set of derivation corresponds to a union of clauses. So let's try to count how many clauses are there in each of these union of clauses that are required in the derivations, right? We're saying, well, I cannot actually use more than 10 times d clauses in each of the derivations. That's what this claim is saying. Okay, good. So, before even going on to prove this claim, I think it should be somewhat intuitive, right? For example, so what's the rough? Maybe let's see what's the rough idea. So before doing the proof correctly, the rough idea is that because of expansion, if I take this union of clauses, each of these union of clauses should actually contain a large number of variables. Because of the expansion properties of the instance hypergraph, right? But remember that in the derivations, I'm only deriving degree D monomials. So I'm only using the unions of clauses, right? Whose XORing gives me at most D variables, right? And so what that means is that, because the XOR contains at most D variables, and because the hypergraph is expanding, I shouldn't really have used, a large number of clauses in the derivations. Okay, so we'll formalize this idea, but, hopefully this is, somewhat clear that it has to be a consequence of the expansion of the instance hypergraph. Okay, So, because I didn't quite write it, so let's erase that. So proof of claim. So, let's argue by contradiction. Suppose, this is not true, right? So we did these derivations in order, right? There was some fixed order that we did the derivations in. Let's say, let's pick the smallest I such that, ui exceeds 10d. Okay. Now, how was ui derived? How did, the correspond? So ui corresponds to some derivation, let's say x si equals b sub si, right? So how was this derived? Well, our derivation rule was that we picked some already derived constraints, already derived hard constraints in the set of derivations, and then, two of them, and then, XOR them out. And when did we do that? Well, as long as, the XOR contained at most d variables, right? Because we are deriving only d monomials. So let's remember, let's say that ui was xsi, equals b sub si. Most of the complexity, by the way, in all of this proof is notational. Okay, so hopefully, if I say things, multiple times, it would make sure that everything is clear. So let's say that ui was the derivation. Ui is the collection of clauses that correspond to the constraint xsi equals b sub si. Okay, how did we obtain this? Well, there was some. Then there are jk less than I, such that uj, which corresponds to the constraint xsj equals bsj, and uk, which corresponds to the constraint xsk equals bsk. Okay, and I XORed out these two. I XORed out these two constraints, which must mean that xsj times xsk equals xsi, right? And in fact, the union of clauses that corresponds to x sub si is simply, union of, or actually the XOR of uj and uk. Okay, so hopefully this notation makes clear. Please feel free to stop me, okay, if this is unclear. But I'm just, trying to understand how did this derivation ui come about? Well, I must have XORed out previously derived constraints. If I XOR out constraints, I can relate them to the set of clauses I'm going to use. And so, this uj XOR uk is just basically the union of uj and uk minus the intersection of uj and uk, because, I don't have to use the clauses that, uj and uk both used. Okay, good. So that's the derivation. And I know that, uj and uk were actually at most 10d, because ui is the smallest, the clause which exceeds 10d in size. So I know that uj is at most 10d and so is uk. Well, that means that ui is at most 20d. Okay. So, I know that ui is I is the smallest index, is that ui exceeds 10d, but, I just proved that it can't exceed it by too much. It's at most 20d in size at the very least. Okay. Very good. So why is that useful? Well, the point is that this is a small, like, so remember 20d is, much, so 20d is smaller than 20 times d. D was eta n by 100 by my choice. So this is much smaller than eta n. Okay, so ui is a collection of at most eta n constraints of I, right? And so, by expansion, I know that the union, or actually the XOR, sorry, I guess just state it. The union of j in ui, cj, is of size at least 1.7 times the number of constraints in ui. So far, so good. So, I just, I convinced you that ui, even though it's larger than 10d, it's at most 20d. 20D is smaller than eta n, so this must be an like this collection of hyper edges that I have from the instance contains at most eta n edges. I know that if I take the union of these clauses, they must contain 1.7 times UI unique variables. Okay, but now I am in trouble because you said that UI is of size at least 10D, so this is bigger than 1.7 times 10D, which is much bigger than D. Okay, so this contradicts. And so, I couldn't possibly have derived. So what does it mean? It means that, if I look at product J in CI, product I, oh no. See, the notation is all the hard part here. So let's say J in UI, K in CJ. If I look at, this monomial, then what we proved implies that, this XOR is a monomial of degree bigger than D. Actually, degree bigger than 17D, so certainly bigger than D. And that's a contradiction because, we were only deriving degree D monomials. So we would never have come across UI in the first place. So this is a contradiction. All good? So that's it, right? Like that was a simple consequence of expansion, that we can never have conflicting. Oh wait, I guess we didn't complete the proof. Sorry, too quick. We proved the claim that each UI, the number of constraints that we use for any of the derivations in the set DER is at most 10D. That's what we proved. Okay. Now let's complete the proof. So let's copy this. Oops, where did it go? Man, Scribble is weird. Okay, so now come back to the proof of the lemma. All right, I'm just gonna write it again. So remember, we had these two sets of constraints that somehow, derive the same thing. Right, and we said, okay, let U1, U2, U1 prime, and U2 prime be the corresponding collection of clauses, that appear in these derivations, right? So now let's understand what this means, okay? So we know that each of these UIs is of size at most 10D. Like that's what we established in the claim above. So if I look at the collection of clauses in U1 XOR U2 XOR U1 prime XOR U2 prime, then it contains at most 40D variables. And by our choice of D, this is again smaller than eta n. Good. But now let's look at what the XOR gives. So x s1 times xt1 must equal x s2 times xt2 under what we did. So this actually equals, or maybe I can write it without monomials as saying that because s1 XOR t1 equals s2 XOR t2, if I look at the variables appearing in the clauses u1 and u2 and u1 prime and u2 prime, then every variable must appear an even number of times. Right? Because S1 XOR T1 equals S2 XOR T2. The only way that can happen is if every variable that appears at least once, in fact, appears at least twice, and in general, even number of times. That's the only way, that S1 XOR T1 can equal S2 XOR T2, right? What does it mean? It means that the number of number of variables in this set U1 union U2, or actually just the XOR, the number of variables in this is at most, so each constraint, has 3 variables, right? So if each constraint contributed 3 variables, then I would get 3 times whatever is the size of the number of clauses here, right? But because each variable must occur 2 times, I am double counting the variables. So the number of variables in the union of constraints appearing in the set is at most 1.5 times the set. But this is again a contradiction of the expansion property, because we said U1, like the collection of clauses U1, U2, U1 prime, U2 prime is a set of size at most 40D, which is much smaller than eta n. It should actually cover 1.7 variables per constraint in it. But because every variable must appear twice, we've in fact established an upper bound that it can only contains at most 1.5 variables on an average per constraint appearing in it. This is a contradiction, so this can't quite happen. Okay, so basically, again, like the notation might be a bit complicated, but the idea is the same, that if you take any not too large a collection of clauses, then in fact they must cover a 1.7 variables per clause, or something strictly bigger than 1.5 variables per clause or per constraint, right? While if some like what's the idea, like if you have 2 sets of clauses that XOR out to the same thing, then they must cover each variable twice. So they can only contain 1.5 unique variables per clause on an average. On the other hand, expansion implies that this cannot happen, and so we just like combine these 2 facts together to derive a contradiction. So the first claim was just to make sure that we are applying this expansion fact on not too large a collection of clauses. But good. So what does it mean? It means, so if we stop here, then what have we concluded? So we concluded that the set der D is well defined. Okay, very good. So now let's go back to how we were defining our pseudo distributions. So we said if x sub s equals bs appears in the set of derivations, then we must set pseudo expectation x sub s as b sub s, right? In fact, the way we have set up derivations, the following extra property holds true. If xs1 equals bs1, xs2 equals b sub s2 was used to derive this constraint, then in fact we are forced to choose a value for the monomial x sub s1 times x sub s2, which is equal to the product of the values we gave to the individual monomials, right? You're all still with me? This is just the consequence of the derivation process that we just defined. Okay, very good. So now we in fact may not have derived all monomials, right? We derived some subset, but many variables may not have been defined. So these were constraints where our hands were completely forced. These are the only values we must choose for the monomials that appear in the set of derivations. What about the monomials that do not appear? So, remember we are trying to construct a object, that is needed in the proof of Grigoriev's theorem. So it's up to us to decide what happens to, the monomials that do not appear in the set of derivations. Here is, some simple thing I'm going to do, which may appear, just like a simple guess, and which is, to set every other monomial 0. So for all the monomials where my hands weren't forced, I just set them to 0. And so, there are various retrospective justifications one could give for this choice. And everybody has their favorite one. Some would say that, this is some expression of the maximum entropy principle. Just somehow, if I have, like somehow one could think of it as saying the following: all the derivations we made in some sense is our knowledge about what, a pseudo distribution must satisfy. We have no knowledge of other monomials because, well, we failed to derive anything in this simple process. We could conjecture that, if I don't have any information, then, I should set it to, in some sense, maximally an uninformative value. So if I don't set it to 0, in some sense, I am biased towards one of the values, but because I had no information, I'm going to set it to 0. But you can ignore all of this discussion because, this is just a guess, a retrospective justification. There is no mathematical reason I know for what I'm doing this, except for the fact that it works, okay? So there are various, guesses I could make here for why we are doing this, but the only reason we can do this is because it works. So let's just actually do a proof instead of like discussing why this is a good choice. But now I have completely defined a pseudo expectation to you. That's the problem. That's the point, right? Like with this guess, the pseudo distribution is completely defined. So, I just look at all the constraints that were present in the set of derivations. I set them to whatever the value the derivations gave them. The rest I set to 0, and that's it. Okay. So let's, prove that this is in fact a good pseudo distribution. The last remaining point. Oh, I guess there should be only one theorem. So let's call this a lemma. So remember, D is this number which is smaller than, some sufficiently large constant, smaller than, the threshold for my expansion. Then mu is a degree D pseudo distribution that satisfies e twiddle mu 1 is 1. That's actually not that surprising. That's in fact the value I'll set it to. So, both these conditions are kind of satisfied trivially because that's how we constructed the pseudo distribution. The only non-trivial property to prove is like, why is it in fact a pseudo distribution, right? In fact, so let's maybe say that the only, so, 1 and 2 are satisfied in some sense by fiat. So the only non-trivial property, so what remains to prove is this non-negativity property, which says that, the pseudo expectation of every square polynomial must be non-negative whenever, whenever P has degree at most, D by 2. So that's all that remains to prove. So let's, prove it. So, again, I don't want to maybe make too many non-mathematical statements, but somehow in the experience of constructing all these sum of squares, lower bounds, which all amount to constructing appropriate pseudo distributions, this is the hardest step. Usually it's usually it turns out to be relatively simple or at least doable to come up with like reasonable guess for a pseudo distribution. And what you then, struggle for long hours, weeks, months, etc., is, proving the, positivity property. And, some people who are in the audience here already have struggled and, with these kind of theorems. Our struggle would be very short, okay? We'll actually complete a proof right away. So this is, one of those easy instances, where the positivity proof is not so hard. So here is how we're going to argue, okay? We're going to define an equivalence relationship, equivalence relation on the set of all monomials of, degree at most d by 2. And what's this relation? So, remember what an equivalence relationship is? Equivalence relation is, I have to prove that, if that, so it's like I'm like splitting the set of all degree at most d, size at most d over 2 indices or subsets into, groups, and I'm proving that it's an equivalence relation. So what's the relation? So I'm going to say that, S and T are related under this equivalence relation if okay. So what does it say? That it means that, I gave you a definition of a pseudo distribution. This equivalence relationship, equivalence relation splits the monomials into equivalence classes based on the relation that S and T are in the same class if the pseudo expectation under this definition mu of the product of XS and XT is, non-zero. Okay. And remember, the way we constructed this thing, the only way the pseudo expectation of XS XT is non-zero is when, XS times XT was, derived in the set of derivations. So this is, if and only if XS XT appears right, like that. That's because that's how we constructed the pseudo distribution. So that's what must happen. Okay. So why is this an equivalence relation? So, this is simple, but let's make sure that, we are not fooling ourselves, because there was an issue with the definition earlier, and we spent a lot of time to make sure that the definition was reasonable. So let's make sure that, this is an equivalence relation. So what do you need to check? Well, you need to check reflexivity and transitivity. So S must be related to S. Why is this true? Well, this is certainly non-zero. So that's good, right? And we have to check transitivity. Suppose S and, S prime are related, and S prime and S double prime are related, then we must prove that S and S double prime are related, that they are in the same class. Why is this true? Well, let's understand. This is really a comment about, our derivation procedure. If S and S prime are related, when are they related? They are related if the XOR of S and S prime is a monomial of size at most, D, right? Because that was our derivation procedure. So S is related implies XS times, okay. Again, we can do this without referring to monomials. S XOR S prime is a set of size at most D, right? That's what our procedure was. So the only way we put, the only way S and S prime are related, if, their XOR is a collection of variables of size at most D, that's the monomial they will derive then, right? And similarly, S prime and S double prime are related if S XOR S double prime is of size at most D. But this, is trivially satisfied for S and S double prime, because S and S double prime are sets of size at most D by 2. So it definitely holds that the XOR of, the symmetric difference of S prime and S double prime is a set of size at most D. Right? So in my procedure, if XS and XS prime got a value, then XS times XS prime got a value. Similarly, if XS prime and XS double prime got a value, then in fact, Okay, so let me, so okay, so they derive a set of size S4T. Let's maybe be even more careful. So now I have to prove that xs x double prime was set, like the product of these monomials was given a non-zero value in the set of derivations, and this is true because right, and I gave non-zero values to xs times xs prime, and I gave non-zero values to xs primes times xs double prime. So in fact, our procedure guarantees so this is a monomial of size at most d. So I did give it a value, and I gave it in fact this value. And because both of these were non-zero, their product is non-zero. Okay, good. So hopefully it's not too hard to convince yourself that this is in fact a legit equivalence relation. Very good. So now for every class, so like, because equivalence relation, it splits all monomials of size at most d by 2 into a bunch of classes. That's let's call the classes R1 up to R sub n. Choose some representative for each class. Let's say S1 up to S sub n. So pick some set that lies, pick some set of size at most d by 2 that represent that class. It doesn't matter which one you choose, just pick one, right? And then observe, by the way we define the derivations and the way we gave values to the pseudo distribution, if you take any S and T that lie in some equivalence class, then actually equals oh wait, I called it SI. Still good? This is because I can write the monomial xs times xt as xs times xsi and xsi times xt. And the way my procedure gave them values was, so I can derive the monomial xs times xt by, taking xor of xs times xi and xi times xt, right? Both of them, must be derived because s and si are in the same class and si and t are in the same class. And so I must give them, in fact, a value which is product of the values I gave to these individual monomials. Still good? Okay, very good. On the other hand, if S belongs to Ri and T belongs to Rj for I not equal to J, so now, if two of the, sets actually live in different equivalence classes, then in fact, by the way we constructed the equivalence classes, this must be 0. Why is that? Well, if it was non-zero, then I would have put them in the same class. So if they are in different classes, it must mean that their product gets a 0 pseudo expectation. Okay, very good. So now, we are basically done. So let's complete the proof now. So these are the only two properties I'll use. So now, let's analyze what happens to p square. So the way I'm going to look at this, the p was a polynomial I'm trying to, prove non-negativity of. Wow, man. Oops. Okay, should have some better light. So let's, in fact, write down p. So, any polynomial p of degree at most d by 2 can be written as a sum over all, its monomial representation, right? And S is of size at most d by 2. That's how any polynomial looks, right? Now, I actually I have split all the monomials of size at most d by 2 into a bunch of equivalence classes. So what I'm going to do is split the polynomial also according to these classes. Okay, so let's call each of these inside polynomials as p sub i's. So P sub I, in fact, is a linear combination of only the monomials that appear in the ith equivalence class. Okay. Very good. So now let's understand what happens to the pseudo expectation that I give to P square. Well, it's the pseudo expectation that I give to the square of the sum of PIs. That's very good. So let's understand what happens now. If I expand the square inside, I get this expression. If I not equal to J, then what is the pseudo expectation of PI times PJ? Can somebody unmute themselves and tell me what they should be?
Zero.
Right, because I can write down Pi times Pj as in this in this expansion. So what's Pi times Pj? Pi times Pj is the product And now the point is that, every product of monomials where one of them is in one equivalence class while the other is in the second, that product must get a zero expectation under my definition. So the property 2 implies that this must be 0. So I only have to worry about, this individual square terms. So now, we've reduced our problem to proving that, E twiddle of Pi square is non-negative, where Pi is a polynomial whose monomials are all in the same equivalence class. Okay. So now let's finish that job. So now we have S and T in Ri, PS, PT, XS, XT. So now let's use property 1. Okay. What does property 1 say? Property 1 says that, the pseudo expectation of the product of XS times XT actually equals, because they're in the same equivalence class, I can relate to it, to the product of this, fixed representative monomial with, S and T. Right? This is the property that we stated and discussed the proof of here. Right? That's property 1. Good. But now we are done, because so I can write this whole expression as simply and because it's a square, it's certainly non-negative. That's it. That's the proof. I wonder if it's anticlimactic, but that's it. Okay, so I have, some, I guess some comments planned, but I can wait for that for like 5 minutes. Let's see if there are any questions, So somehow, so actually, this again is not a mathematical claim, but this might actually be the simplest sum of squares lower bound you might ever see. So that's good. By simplest I mean something you can hopefully do in like one lecture, which we did. In the next lecture, we'll try to put something more general, but we won't actually give complete proofs. Yeah, any questions?
So I didn't understand the contradiction you showed above. You showed that union of the clauses will have at least 17 D variables.
You didn't finish this argument.
Yeah, but then you concluded something about XOR of the clauses. So.
Here?
No, above this. Yeah,
right
here.
Okay, let's see. So So let's maybe go over the proof maybe once again. So, okay, what are we trying to prove? We are trying to prove that, if you look at the derivations, look at the constraints that appear in derivations and look at the union of clauses that corresponds to each constraint, then in fact, you couldn't possibly have used more than 10D, constraints in them. That's what we're trying to prove, okay? So we're saying, suppose this is not true, then, just pick like the smallest, the first derivation in this sequential process, which uses more than 10D clauses or 10D constraints, okay? Then we argued that in fact, even though it uses 10D constraints, it cannot use more than 20D constraints because it itself was derived by using some previous derivations and each of them was at most 10D large, right? Okay, so let's say Uj and Uk were the constraints and, we convince ourselves that in fact, UI is a collection of a small number of clauses now, right? Very good. So now, okay. Good. So now what are we saying? We are saying, sorry, 1 second. Okay, so now I see what the confusion is. I think I did the quantitative bounds wrong. So okay, at least I didn't complete the proof, it seems. So the union of CJs you agree is at least 1.7 times UI large. This is just, applying the expansion property. I can apply that because, UI is a collection of at most eta and constraints, right?
Yeah.
Still good? Okay, very good. So now, let's try to understand. So I guess I concluded that the XOR, without actually justifying, I concluded that, the XOR of the clauses or the constraints that appear in CJ cannot be of size, at most D. That's what I concluded, right?
Yeah.
So let's understand why not. I'm saying that, let's, so when I take XOR of the constraints in, this set here, the union of CJs where J come from UI, right? Then which variables disappear? Well, the variables that appear, at least twice, right?
Yeah, sure.
And the variables that appear at least once will, continue to remain in this XOR of CJ, correct?
Yeah.
Okay.
At most once.
Yeah, exactly. I mean, if it's 0, then it cannot appear. But yeah, so anything that appears, at least anything that appears at most once will, will contribute to this XOR of CJ. And so now the point is this. I claim that if the union is 1.7 times UI large, then in fact, this must be at least, so let's maybe do the contradiction a little below. This must be at least 0.2 times UI. Okay, and this 0.2 is simply, 1.7 minus 1.5.
Okay.
Okay, do you see why?
It's the same argument we did below, right?
Exactly, right. Like if you repeat, then, each constraint can only contribute 1.5 variables, right?
Yeah.
So the only way, so in some sense, the only way my union has 1.7 variables on an average, if each variable, constraint contributes 0.2, 0.2 fraction, unique variables on an average, right?
Yeah.
And so now, I'm good because, okay, so I guess I didn't complete this argument earlier. Thank you for reminding me. So this is 0.2 times the size of UI, which is 10D, which is bigger than 2D.
Yeah.
Well, and that's a contradiction because this was supposed to be, at most D.
Okay.
Good. Does that make sense?
Yeah.
Okay, very good. More questions? Okay, so now, given that there are no more questions, I mean, there can be more questions and we'll take them up after 6:50 as usual. Let me make, some basic comments so that, we are prepared for the next lecture. So let's first understand, what did we use about the instance and where did we use it? So where did we use the randomness of clauses? Of, the sets of variables that appear? Well, we used it to prove expansion of the resulting hypergraph, right? Well, we claimed it, we didn't prove it today. right? So randomness in the choice of this size k sets is important to prove the expansion of the resulting hypergraph. Where did we use the randomness in the right-hand size? Again, can someone unmute and tell me?
Epsilon upper bound.
Right, exactly. This was used to prove that true value is small. So upper bound on opt. Okay, so in some sense, the two pieces of the random, the two random pieces of the construction were used in some sense in two separate ways. The randomness of the k tuples that appear, we use it in the expansion, and the randomness of the right-hand sides we use in, to just bound a true value. It never appeared in the construction. In particular, note that our construction is valid for any arbitrary choice of b sub i's. Like the pseudo distribution exists for an arbitrary choices of b sub i's. It doesn't need to be random at all. I mean, to construct a gap, we just chose it randomly because we wanted something which has a true, a small true value. But the construction is valid for an arbitrary. So I guess maybe I'll make this point. Construction of mu works for arbitrary BIs. Doesn't need randomness. Okay, very good. And the next point I'm going to make is something that I hinted at the beginning, which is that we set out to prove, just some lower bound. We were going to be happy with, any large round sum of squares lower bound, but we ended up proving something nice. We actually proved that not just some arbitrary weird pathological instance of, KXOR is hard. We in fact proved that a random KXOR is hard. So what did we end up proving? We showed an average case hardness. Notice that this should be somewhat surprising to you. In the last class, we studied a very general algorithm, but one consequence of that was that random instances of max cut, are not hard at all. Remember the sequence of claims that implies this? So we said, low threshold rank graphs are easy. And, in particular, expander graphs are very, very easy for max cut. And we proved, we sketched at some point that, random graphs are very good expanders. So, for k equals 2, which corresponds to the max cut case, random instances are not hard at all. We can get like way better than, even 0.878 approximation. But here is a issue, that occurs at k equals 3 and beyond. We are saying that if you look at, 3 XOR and 4 XOR and so on, then in fact, even random instances are extremely hard. So hard that, it requires omega and degree to even beat the random assignments, performance. Okay.
This is for SOS only, right?
This is for SOS only. Yes. All the comments are really just about SOS. Yes.
Like if you want to just approximate, you can just pick a random instance and it's almost optimal, right?
Sorry, what?
If you want to just approximate the solution, like not with SOS.
Good. Yeah, you're talking about computing the optimal value, but of course there is not much going on with that. As you observed, any assignment is actually going to be good. But we are interested in integrality gap, and in fact, we'll clarify this difference next time. There is a sense in which you can ask for certifying the best possible upper bound on the value of the instance. For example, can I give you a short proof that the value of the instance is at most half or close to half? That, you can't do by just producing an assignment, right? Producing an assignment just guarantees that, you found something, some assignment that satisfies, some given number of constraints, but it doesn't tell you that there may not, it doesn't rule out the possibility that there's a different assignment that satisfies many more constraints, right? Our algorithms were actually so far giving us certificates. They were proving to us, they were giving us, efficiently verifiable certificates that the value is small. And I guess what we are saying is this was very easy for random instances of max cut, producing a certificate. But for k bigger than or equal to 3 and beyond, we don't expect this task to be easy at all. It certainly isn't easy what we proved in SOS today, but in fact, we don't expect any algorithms for it. Does it make sense?
Yeah, thanks.
Okay, very good. So in fact, we proved that random KXOR is not just hard, it's like maximally hard. right? By maximally hard, I mean that, there is no way to beat in polynomial time the performance of the random assignment, okay, in terms of, the search problem. So you could ask, which other CSPs. So remember we defined CSPs earlier. So instead of the KXOR predicate, you can, so what's, okay, maybe I can remind you of what CSPs are. So, CSPs are, defined by some Boolean function like this. So, just basically, it's some assignment to K variables. Some of them are satisfying, some of them aren't. And then, each instance is defined just like we did today as by CI, a collection C1 up to CM, right? And the goal is to, and each, okay, so sorry. So these are, subsets of n. Each of them, has some negation pattern. Let's ignore it. Right, and then the goal is to find x in, the set of assignments such that, Ci of x, is satisfied. So more concretely, P, the predicate P is satisfied. So, today what we did was for the XOR predicate, but you could ask this question for, arbitrary predicates P. And you can ask, which predicates are maximally hard? For which predicates, is it impossible to beat the random assignment? So, we saw some examples already, right? Like max cut is not hard. Max K XOR for K bigger than or equal to 3 is maximally hard in SOS world. You can ask which other predicates have this property. So it turns out that we can basically completely characterize this set. And in fact, you can ask this question in two different ways. You can ask this question for, random instances. But you can also ask this question in worst case. And we actually know complete answers for both these questions. And the answers are different. And so one thing that we'll do the next time is, describe the answers to the first set of problems here, and maybe just state the answer to the second set of problems here, because our interest, in the next class would be, average case CSP problems. Yeah, and we'll see some ideas that go into characterizing which CSPs, at least the random instances of which CSPs are maximally hard. We'll see, why this is interesting. We'll see like several applications of this. For example, okay, I guess I'll maybe discuss this more next time, given that it's 6:53. But we'll both see the characterization of which CSPs are maximally hard, and we'll also see applications of this hardness. Like in particular, like why should we care that we can completely characterize this set? So let's formally call this the formal end of the class, and then we can have more discussions, ask questions. All right, questions?
Oh, hi, Pravesh. I have a question.
Yes.
Yes. So can you remind me like which predicate is worst case hard but not random, but not high in random? And I suppose you're talking about UG Harness.
Right. I mean, I'm only talking about SOS hardness because that's kind of what I care. But you're right. Even that is actually not understood unconditionally. So I guess complete answers for both. For worst case, this is only conditioned on the unique games conjecture, as Jeff pointed out. So you're saying what's a predicate that is worst case hard but not average case hard? Good. So these are like somewhat contrived. I think there might be a simple example, but one example is so there's a predicate that Aaron constructs in a recent paper, maybe 19, linear threshold predicate. So it's a function of the following form. So P, this predicate is it's some, I don't even remember the arity. I think it's some large number. And P has a form that so P is described by some linear function L and threshold tau, and P of X is 1 if and only if Lx is bigger than or equal to tau. Okay, so this is what is called as a linear threshold predicate, because it is it takes the value 1 only when a certain linear threshold linear function is like larger than some threshold. And what Aaron proved is, so what Aaron Potechin from Chicago proved last year is that assuming the unique games conjecture cannot beat random assignment, for some contrived family of instances of this predicate of the CSP with this predicate. On the other hand, you can provably show that random instances with the same predicate are not hard, at least not maximally hard. So we'll study some of these theorems the next time, but the relevant theorem here is due to Alan O'Donnell. So O'Donnell is Ryan O'Donnell and David Whitmer from 2015, and they proved that well, they didn't quite prove it for Alan's predicate alone, but they proved a theorem that implies that Aaron's CSP is not hard on average. So in other words, you can in some sense beat the guarantees of the random assignment on random instances. And actually, this is just to concretely answer your question, but there is basically some characterization of both these sets that we have. Yeah, I guess because I want to discuss it next time, I maybe don't want to spend too much time on this today, but the characterization for the random instances turns out to be this property called as pairwise uniformity. Maximally hard CSPs are those with what are called as pairwise uniform predicates. And there's a similar, I mean, not similar, but there is some characterization of predicates which are hard for the worst case CSP problem. And it's a strictly larger set. Yeah, we'll do this in more detail the next time. But yeah, they are they're provably different classes. More questions?
I have kind of a vague question. So
Sure, yeah.
One, so one implicit assumption in the thing that we proved today is that there's this C times opt minus val of I function, and we're showing that this does not have a degree D sum squares proof.
Right.
Why is this the only function that you would want to rule out? In some sense, like, why is there a unique function which tells us something about the algorithmic limit of of SOS here?
So this is at least, I mean, there are multiple ways to interpret this question, but you admitted already that it's a vague question. So let me, give, some potential answer. So, okay, so here's what Anish is asking, saying, okay, we tried to construct certificates for C opt I minus val I. But I suppose you could do different things which kind of tell you the same thing. For example, you could consider certificates for C square opt square I minus val I square. Okay, and informally it says the same thing. It allows you to upper bound the value of the instance, like the maximum number of constraints that any assignment can satisfy, right? So in some sense, this is as good as this function, even though it's a different function, it's just as good, as the first function. And what Anish is pointing out is that we don't seem to have proven a lower bound for, choices like this. Well, actually we have, we just didn't state it. So the lower bound we proved today actually, works for any such function. Okay. And the reason I did not state and prove it in this form is because I need to define what are called as constrained pseudo distributions. And I guess that's my plan. That's part of my plan for the next time. So we'll see what we proved today actually, manages many other formulations that you might come up with, including, this example over here. But in the larger scheme of things, Anish, the answer is obviously that we will not have ruled out all formulations. Okay, why not? Well, because, there might be a world in which, you take the KXOR problem. So, there might be, so, okay, so, so maybe state it this way, such formulations are actually ruled out. So, our theorem from today says that, not only is C opt I minus val I not a low degree sum of squares, but in fact, this other function is also not a low degree sum of squares. Ruled out by, today's theorem. But I'm saying that, you can't be like, completely general in what you expect to prove here. Because, for all we know, P equals NP. And then, there is a reduction from 3 XOR to bipartite matching or whatever, like, I don't know, even max cut problem. So, let's say, there is the reduction to, checking bipartiteness, which is like detecting if the max cut is 1 or not. And, so you could do this reduction and then write the formulation that literally checks bipartiteness with SOS. That would be a very valid formulation if this reduction exists, but I don't know it exists. And I can't hope to prove a lower bound that, allows you to make such reductions, right? Because at least proving P different from NP was not part of our plan today. So yeah, so I guess what I'm saying is that, unless you want to prove unconditional lower bounds on all algorithms, you can't hope to, rule out every possible formulation. You can, rule out some class of formulations, and in fact, that have a nice description. They are like low degree equivalent to this canonical function over here, and we'll discuss why what we proved today, in fact, implies, even this formally stronger fact.
Mm-hmm.
Does that give you the right answer?
Yeah. So a follow up. So if you assume P not equals NP, can you show that all possible formulations of this form are ruled out?
Yeah, I mean, yes, just because if there is a low degree certificate, which has small bit complexity, then we can find such a certificate in polynomial time. So that would be a contradiction to, P not equal to NP.
Okay, that's easy.
Yes, it is. Yeah, so maybe one point that comes out of Anish's question is interesting to observe that if all you wanted was that to prove that assuming P different from NP, prove that KXOR is maximally hard, then there's nothing to do because you can just simply apply Hostad's theorem and get the theorem in the first 15 minutes of the class. So there's nothing really to prove if you were okay with a conditional lower bound. The effort we spent today was to prove an unconditional lower bound. We proved something that holds regardless of the status of P P and NP. So for example, even in a fictional world, well, not fictional, even in some, hypothetical world where P equals NP, the lower bound we proved today is valid. There might be a different algorithm that solves the KXOR problem optimally, but sum of squares isn't it.